Hello friends, so in this next video, we are going to discuss buck regulator. So far we have discussed that DC-DC regulator is using the power electronic switches like BJT, MOSFET, IGBT, which are switched on at high frequency to get a variable DC output. So in this, we are going to discuss the first variety. So what is DC-DC switch mode regulator? It provides regulated voltage from an unregulated DC voltage. This is the flow that let's assume we have a single phase or three phase. From that we get the pulsating DC from uncontrolled rectifier. Then we use filter and then DC-DC regulator. So the last part, DC-DC regulator, is what we are going to discuss. And in this video, we are going to discuss the buck regulator. So there are three types: buck regulator, that is step down; boost, that is step up converter; and buck boost, that is step up down converter, right? So in this video, we are going to discuss buck regulator. So this is what we have already discussed in our previous video, that chopper as a switch is shown over here with the output V0, which is delta times Vs, and delta is nothing but the duty ratio control. So this D or delta is used in literature as a duty ratio control, which is ratio of T on divided by TS. T on is the on time of the switch and TS is the switching time interval of the switch. And what are the switches? BJT, MOSFET or IGBT are used in this DC-DC converters as a power switches. So volt second balance, also we have already discussed this concept, that there is going to be a large inductor in this circuit, and so when a steady state is achieved, when a you can say equilibrium is achieved, then in that situation the current through inductor, the voltage across inductor over a period of 0 to TS is going to be, the average of it is going to be 0, or you can say the area under the curve over one period for the voltage with respect to time curve is going to be 0. So that is the principle which we are going to use to derive the output equation of the buck converter. So now what is this? This is the volt second balance. So this area, these two area over one time period is going to be equal, and that is the principle which we are going to use. So now buck converter circuit. So this is the buck converter circuit. Here we have used BJT as a switch. For example, I have kept over here BJT as a switch. We can use IGBT or MOSFET also as the switch. So when the device is used in this fashion, it gives output voltage smaller than the input voltage. Here BJT, MOSFET or IGBT can be used as a switch. Now let's see the operation. So when Q1 is turned on, how do you turn on? It is turned on by giving the base current IB. So when Q1 is turned on, it is as good as a switch is turned on. So then the diode D1 is reverse bias, and we get voltage across inductor as Vs minus V0. Let's assume that this is happening for a very sufficiently long time, and it is with the frequency say Fs and time period Ts, and a steady state or equilibrium is achieved. Under that situation, these equations are valid, right? So this VL is Vs minus V0, where Vs is supply voltage which is available over here, and V0 is the output DC voltage. So in this situation, when switch is turned on and supply voltage is applied, of course the current through inductor is increasing, and let's assume it's increasing from one value I1 to say other value I2, right? So this is going to be the situation circuit when the switch is on, when the Q1 chopper is on, and in this situation for D times Tn, that is for T on period, the voltage across inductor is Vs minus V0, where Ts is the switching period. So that is what happens in a buck converter when switch is turned on. Now when switch is turned off, you can see over here, when Q1 is turned off, how do you turn off? You turn off with by removing the base current. So when you turn it off, this is disconnected, and as the current through inductor cannot vanish, so this D1 becomes forward bias, right? So D1 is forward bias, which is called freewheeling action. And IL, of course, as there is no energy, so whatever is stored energy in inductor, that is 1/2 Li square, so that is dissipated in resistance, and so we can say that current reduces from I2 to I1. So what is voltage across the inductor? It is going to be minus of V0, right? And this is the circuit, equivalent circuit when the Q1 is turned off. So this is how the arrangement looks. VL is equal to minus V0 and current through inductor reducing from I2 to I1. So as it is reduction, so we can say the inductor voltage is negative over here, right? So we can see over here for T off, that is 1 minus D times TS, the inductor voltage is equal to minus V0, right? Now let's see the waveform of this buck converter. So we can see this is the converter, and when it is turned on for D times TS, VL is VS minus V0, and when it is turned off for 1 minus D times VS, VL is equal to minus V0. These are the waveforms which are established at a steady state when the current and voltage at the output are stabilized. They are in equilibrium. They are in steady state. At that time, for D times TS interval, the output, voltage across inductor is Vs minus V0. And for 1 minus D times TS, that is T of time, the output is the DC voltage across VL is minus V0. And this is the whole duration switching time interval TS. This is the current through inductor, and this is how it varies, right? So when the switch is turned on, current increases from I1 to I2. We are assuming linearly it is increasing. And when it is switched off, it is reducing from I2 to I1. So ultimately, this is going to be the volt-second balance. We are just considering the voltage across inductor waveform and one time period. So we know that applying the volt-second balance in a one time period, the average voltage across the inductor is to be 0, or the area under the curve should be 0. Or should I say this Vs minus V0 into dTs is this area plus this area is going to be 0. So if you substitute this and simplify mathematically, we get output voltage V0 is equal to D times Vs, where D is nothing but duty ratio, duty cycle ratio, which is T on divided by Ts. And it can be in the range 0 to 1, right? At the most, it can be 1. Generally, it is less than 1, and that's why output voltage is always less than the supply voltage. That's why this converter gives variable DC, but step down, that is the output DC lesser than the input DC. And the variation can be achieved by controlling the T on time, that is duty ratio D. Right? So let's summarize the buck converter. So buck converter is a simple arrangement where a power electronic power switch like IGBT, MOSFET or BJT is connected as shown in the circuit. And through a T on T off operation with very high frequency, 1 kilohertz to 3 kilohertz, we achieve the voltage at output reduced or smaller than the input voltage. BJP, MOSFET or IGBT can be used as a switch. In various conditions, different switches are used. We'll discuss it in our separate video. Variation is achieved through duty ratio control, and this duty ratio control is achieved through PWM technique, for which we'll learn it how to do it in our subsequent video. Switching frequency is generally 1 kilohertz to 3 kilohertz, right? So this is all about a buck converter. Buck converter is first variety of DC-DC regulator used to get voltage, DC voltage reduced or less than the available fixed DC voltage, right? So this is all about the DC-DC converter, buck converter, and we are going to discuss more about the other variety, that is boost converter, in our next video. Please keep in mind, this is for quick review of the topic, for quick understanding. For detailed understanding, one is supposed to go through reference books, good textbooks, and learn this topic in detail, right? I hope you understood and enjoyed this video. Thank you for watching this.